Hey space friend, as you may or may not know, my ship was recently breached by some very judgy aliens. It made me realize we're probably not as far out in the middle of nowhere space as I thought we were, so we should probably work on some of our emergency sensors until we get our external scopes properly fixed. Personally, I'm pretty concerned about being surprise dragged into a star's gravitational field or getting in range of a supernova. So today we're going to use a light sensor and an RGB LED to detect if we're getting too close to a star that we do not want to be owned by. Both of these things typically come in basic sensor kits. In a practical sense, light sensors do things like adjust the exposure on a camera or the auto brightness of a phone screen. The light sensor we're using today is called TEMT6000 and it's only affected by visible light. Any light that we can't see won't have any effect on it. The sensor has a single phototransistor that measures illuminance, where brighter equals more current and darker equals less current. Illuminance refers to how much light or lumens is shining on a surface. The intensity of the light is measured in lumens per meter squared. If you move the same source of light farther away from the sensor, it increases the amount of space that the light has to fill, so it will read a smaller value. We specifically say that the sensor measures illuminance and not brightness because brightness isn't really used for quantitative purposes since it can be difficult to calculate without accounting for distance. If you have a very bright far away object and a dim close object, they could appear to be the same level of brightness. Let's go back to art class in elementary school and think about the primary colors red, yellow, and blue. Then let's throw that out the window and think about the colors red, green, and blue because those are the primary colors when we're talking about physics and light. A good boy named Isaac Newton found that he could use prisms and mirrors to combine the colors red, green, and blue to create white light. He called these colors primary since they were what it took to create a clear white light. The RGB LED emits different colors by combining these primary colors of red, green, and blue. It consists of 3 LEDs, one for each color, and has 4 leads, one for each color LED and 1 cathode or anode. Which one depends on the type of RGB LED you have. To get different colors, we use PWM to simulate an analog output that will provide different voltage levels to each LED. First, let's test out the light sensor. We just need the light sensor module and then 3 male to female jumper wires. Connect VCC to 5V, ground to ground, and the S pin to A0. We're setting the light pin and the light value as integers because light pin is just specifying that it's connected to pin A0. And the value that will be attached to light value is going to be an analog reading between 0 and 1023. The variable light is set as a float because it's going to require a decimal calculation to turn it into a percentage. Void setup is just turning on the serial monitor and then setting the light pin as an input. Void loop is first reading in the sensor data with light value and then converting it to a percentage. If we were to put in that calculation instead of just multiplying by 0.0977, it makes the variable light funky because when we try to print it, it's going to try to calculate integers and floats together. So we avoid this by using the 0.0977 instead of that calculation. Let's use this headlamp to test the light intensity. Okay, zeros all the way around. Put it in front of my head. And depending on how shaky my hand is at the time, we're jumping between the 50-ish% and almost up to 100. Before we try to put both of these modules together, let's see how this RGB LED works. We need the LED module, 3 220 ohm resistors, 4 jumper wires, and the breadboard. Connect a resistor in line with the RGB pins. Red is going to go to 7, green to 6, and blue to 5. Then connect the remaining pin to ground. The setup is all straightforward. We just set the pin variables, color values, and pin modes. Below the loop, we have made this function called setColor that's taking in arguments for the red, green, and blue values. Within the function, analog right sets each LED's values using PWM, so a value between 0 and 255. The way this works in the loop is we call a function and then set our PWM values. Red is the first argument in setColor, so writing 25500 is going to turn red all the way on and then green and blue all the way off. When we call this function in the loop, then the analog right statements within setColor are going to execute. So each color pin then gets the value written to it. After the red LED turns on, then the same thing happens with green and blue. To get these other colors, then we just adjust the values on each LED so that they output the color that they want. Because remember, there are 3 LEDs within this module, the red, the green, and the blue, so we can just tweak them however we want to make these different colors come out. Okay, now we can integrate the 2 modules together. We definitely want to be able to get this working because I do not want to drift anywhere near a supernova. But what I do want is to talk about supernovas, which means it's space facts time. A supernova is the colossal explosion of a star. However big you think supernovae are, they're even bigger than that. One of my favorite XKCD posts prompts the question, which of the following would be brighter in terms of the amount of energy delivered to your retina? A supernova seen as far away from the sun is to Earth, or the detonation of a hydrogen bomb pressed against your eyeball? The answer is the supernova by 9 orders of magnitude. Stars burn fuel in their cores, which produces heat. The heat causes pressure that pushes outwards while gravity pulls inwards. This push and pull is in balance for most of a star's life, but when it runs out of fuel and starts to cool down, those outward forces of pressure drop. When the star is massive enough, gravity takes over and it collapses in seconds. This explosion is called a supernova. Whenever atomic nuclei come together like in the sun or break apart like in a nuclear reactor, they produce something called neutrinos. Bananas even produce neutrinos from the natural radioactivity in the potassium. A neutrino is a subatomic particle that's electrically neutral and has a mass close to 0. While a supernova is unimaginably huge, neutrinos are unimaginably small. The sun is shooting out neutrinos like crazy, so right now you've got about 1 trillion of them just passing through your hand. But they're so tiny that they barely interact with ordinary matter. The ones passing through your hand will only run into an atom in your body once every few years. Because they're so tiny, the concept of a lethal dose of neutrino radiation sounds crazy. How could you possibly get hit with enough neutrinos for it to be lethal? Enter supernovas. When a stellar core collapses, different things can happen depending on how massive a star is. Some can collapse into a black hole, and some can become ultra-dense neutron stars. When a core collapses into a neutron star, 10 to the 57th power of neutrinos are released. 1 for every proton in the star that collapses to become a neutron. This is more than enough to be a lethal dose of neutrino radiation if it ever happened to our sun. Which it won't, because our sun isn't big enough to supernova. Back to the real point, we gotta get this light sensor working so that we don't run into one of those bad boys. We've kept a lot of the same code here, but just added the 2 together. The biggest difference is this if-else statement. If the light intensity gets above 85%, then we want the red LED to turn on to let us know that there's a star emergency happening. Otherwise, we're just gonna cycle the light colors like before. They've got minimal light intensity so far, and then we bring our light slowly closer. The RGB LED is continuing to flash between colors, and then we get above 85. The LED turns red. We're having a star emergency. Being worried about supernovas taking us by surprise because we have no functional equipment to fully scan the area. Not us, because if nothing else, we've got a light sensor. I'm sure nothing's ever gonna go wrong.